This video will look at the Doppler effect equation when looking at redshift. Now, as a reminder, redshift is when the wavelengths of the visible light spectrum change in relation to the Earth from moving galaxies. Now, if they appear redder, we say that they're going to get further away. And if galaxies' light appears to shift towards the blue end of the visible light spectrum, they'll be getting closer. Just like for the Doppler effect, there's an apparent change. If you're stationary, there's an apparent change of frequency of sound from a moving object. As long as you're stationary, it's coming towards you, which is why if you're, say, at the Formula 1, the sound of the Formula 1 car changes as it comes towards you and then gets further away. Now, this redshift change was first observed by Edwin Hubble. Now, Edwin Hubble has got Hubble's law named after him. And this is when he basically said that the velocity of a galaxy is directly proportional to the distance from the Earth. And we might see graphs like this where we've got the velocity of the galaxy on our y-axis and the distance from the Earth. And then when we plot these galaxies on this point, they will appear in a line like this. And they will appear around there. And so we've got evidence here that the universe is expanding. And he noted that the further away they are, equals the faster they are. So the further away, the faster they are. Now, it's important to know when we're looking at redshift that quite often it's measured in small amounts called nanometers. Now, nanometers can be described as 1 times 10 to the negative 9 meters, and that's 0.0001 meters, so relatively small. And we use this equation to look at that, where the wavelength, the first wavelength here, is what we call, this is the shifted wavelength. So that's really the red shifted wavelength. And this is our reference wavelength. And again, this one here was the same as that. That's our reference wavelength. V, on the right-hand side of the equation, that's the galaxy's velocity. More than likely, we're going to have to work this out. And C is the speed of light. And you might have seen another famous equation where it's E equals mc squared. Now, the speed of light is 3 times 10 to the power of 8 meters, or 300,000 meters per second. Now, what were you asked to do with this equation then? Well, you'll be given, more than likely, a little bit of text. And this text you're going to have to work out. Now, this redshifted equation here, this wavelength, this one here, tends to always be the bigger number, unless it's a blue shift where it'd be a smaller number. So look out for the bigger number, and we'll see there that it might be classed as like the observed wavelength, or the redshifted wavelength, or a wavelength that has been redshifted, and we can write that down. So let's say in this equation here we've got a redshifted wavelength of 530 nanometers, and our reference wavelength was 505. We then divide that by the 505, and that is going to be equal to the speed of light, 3 times 10 to the power of 8. So it's on our calculator, you'd have to do 530, take away 505, which is equal to 25, divided by 505, which is 0.049. 0.049. Now we times then that, when we rearrange this equation, that's going to be times by the 300,000 here, which will give us the velocity of this galaxy that's moving in relation to the Earth, and that velocity will be 158,147 meters per second. Now, what if they really want to challenge you and they're going to ask, maybe they want you to work out what the reference wavelength is. And let's say they said the redshifted wavelength is going to be 480 nanometers, but we need to work out that reference wavelength. So they're going to give you the velocity of the galaxy. We know that's going to be 3 times 10 to the power of 8. All right, and they will give it to you as something like 4,687. All right, something like this. So what would we do? Well, we have to use some cross multiplication. So we know, oh my goodness, from here to here. So the first step we'll do, we know it's that 480 take away our reference wavelength times the 300 million, but we want to simplify that fraction. So you can do that simply on a calculator, and if you do that on a calculator, you simplify it, you'll get to 25 over 16. So that'll make things a lot simpler for you. So 480 take away our reference wavelength is times 16. Now another way of looking at that is going to be 16 times 480 take away that reference wavelength, which when we times 16 by 480 we get 7680, and then we take away 16 times our reference wavelength. Now look at the other side where we've got our reference wavelength and going up here to 25, it'd be our reference wavelength times 25, which is equal to 25 times the reference wavelength. So we want to get rid of, on this side here, we want to get rid of that, so that's minus 16, so we want to add 16, but because we've done it on that side, all right, we want to do it on the other side too. And so when we mix these equations together, all right, that will then be equal to, because 16 plus 25 is going to be 41 times that wavelength is going to be equal to 7,680. And then we can rearrange that equation. Well, that's 7,680 divided by the 41, which is going to be equal to 187.3. So 187.3, 187.3. So that's how we can rearrange, using cross multiplication, this calculation here. It's very unlikely though you have to do that. You're just going to have probably to work out the velocity. So it's your redshifted equation here, take away your reference equation, divided by the same one, and then to work out v here, we have to times that by our speed of light, 300 million. Now, I hope that helps you with the Doppler effect equation looking at redshift. Good luck.